感谢两位的精彩演讲。下面有请来自英特尔的首席工程师、首席 SPDK 架构师 Jim Harris 与大家共同探讨 SPDK 项目现状。掌声欢迎。
Hi, welcome to the 2021 PRC Virtual Forum for SPDK, PMDK, and Intel Performance Analyzers. My name is Jim Harris. I'm a principal software engineer at Intel. I'm also one of the core maintainers for the SPDK project. And I'm going to start off today's talks with a State of the Union, sort of where the project is at as a whole. So we're going to cover this in three parts. First, state of the community, what are some of the major milestones we've had, and some metrics on participation. Next, state of technology, so looking at some of the key features that have been added over the last year. And then finally, looking at some of the current and upcoming focus areas for the project, things you can expect to see over the next 12 months. So to start out, no project is really complete without a symbol. So we've got a new SPDK symbol that you'll start to see, you're already seeing, you'll see more in SPDK collateral. This sort of represents a racetrack showing the speed and performance of applications that take advantage of SPDK. Unfortunately, COVID continues to impact the project primarily because it makes it much more difficult to meet together. So, again, we've had no face-to-face summits this year, no developer meetup. These types of events have always been really important to the community as a whole. I know I personally have always enjoyed coming to do talks at the face-to-face summits in PRC, being able to enjoy roast duck in Beijing, and hope that I'll get a chance to do that, maybe next year. So we had 4 quarterly releases again over this last year, including the 21.01 stable release back in January. And we're actively marching towards another LTS release, which we'll have in January 2022, next month. We haven't had any face-to-face summits, but we have been able to have 2 virtual summits over the last year. We had one for PRC last November, and had one here in the US this last summer. And so those are still good for us to be able to get out and kind of talk about the project and things that are going on in lieu of being able to meet face-to-face. And finally, we've been actively trying to use naming and terminology in the project that's more inclusive. So for example, now instead of using terms like whitelist and blacklist, we're using terms like allow list and block list, which are much more inclusive and less offensive. Also things like using primary and secondary versus master and slave when we talk about SPDK and cores and where things are running. And so this is something that we feel is really important, and the project will continue to make a focus moving forward. We like to take a look at the patches, over periods of time to kind of get an indication of, especially the number of committers that we're seeing, and then also like how are the patches being submitted? Are they all coming in from just a small handful of committers, or are they spread out across a broader range of the developer community? And so each of these rows here represents about 1 year of time, so releases over the period of about 1 year. And you can see the total number of patches has been relatively consistent. There's been a drop-off over the last year, but I think that the thing we really like to see is that the number of committers continues to be really strong. We had about 100 committers over the last year, and even more importantly there is we can continue to see that those commits are being spread out across a broader set of the community. So where, early on, almost all of the patches were coming from about 10 committers. Now we can see that they're getting spread out much more broadly across the community. So we're having, not just the total number of committers, but even the number of committers who are even more active is continuing to grow. And when we break this down, we continue to see that PRC is a very big part of the SPDK community, especially in patch commits. So we see there's been about 30 committers from PRC from about 10 different companies. We're really excited to see this and hope to continue to see this grow down the road. Also like to take a look at our GitHub site, who's going out to GitHub to view the documentation, things along those lines, and we continue to see this grow anywhere from 10 to 15% year over year to compared to where we were last year. So next, let's talk a little bit about the technology, some of the main features that have been added since we did our last virtual summit last year. One of the big ones is vfio-user, and you're going to hear Changpeng Liu talk about this much more extensively later today, so I'm just going to give a little bit of an overview now. This is just a framework for implementing PCI devices in user space, and Nutanix has been driving the underlying vfio-user framework and library itself. You can go out to their GitHub site to get access to that. But the way SPDK leverages this is using vfio-user to implement NVMe PCI devices for purposes of serving storage into QEMU VMs. So allowing QEMU VMs to see an NVMe SSD as a physical device, but that the backing storage is actually being handled and processed by an SPDK target process. And so when we look at how this is actually implemented, what we've done is we've taken the NVMF target. So NVMF stands for NVM fabrics. Fabrics meaning, typically meaning network fabrics, so RDMA, TCP, fiber channel. But we've been able to take that framework and extend it to not just network fabrics, but also things like vfio-user. So now the NVMF target is, it's a generic NVMe target layer that can be used not just for network fabrics, but for things like vfio-user as well. And so we're getting a ton of reuse on work we've already been doing on the network fabric side for these virtualization use cases as well. And so this allows us to present the storage to those QEMU VMs. Of course, you need the support in QEMU to be able to do it, to be able to connect to the SPDK target. That work is still in progress. It's not an upstream QEMU yet, but that's being actively worked on by the community, Nutanix, Intel, Oracle, Red Hat. And so you can expect to see that support landing shortly. Of course, there's a lot of similarities here. In the past, for these virtualization use cases, it was primarily with vhost, using vhost to present VirtIO block or VirtIO SCSI devices to VM. So there's a lot of overlap in the use cases, but using two completely different frameworks to be able to do it. So Changpeng actually had looked at doing NVMe over vhost early on, several years ago, and just decided from the work that he had done and interactions with the QEMU community that just wasn't the best path forward. And so that's what sort of led Intel and Nutanix to really start to drive vfio-user as another way to be able to do this for storage. And then we've also added support in the NVMe driver so that you can have a separate process that can connect to an NVMe target over vfio-user. And so this allows you to, for example, have a target that has an SSD, be able to partition it using things like logical volumes, and then have a bunch of different SPDK host processes that can connect to it using the NVMe driver to be able to consume that storage. So next, the scheduler framework. This was added in the 21.01 release back in January. And it allows us to have pluggable scheduler modules. So before we had this, there was no scheduler. You just had a reactor that ran on every core in the system, and you had SPDK threads that were tied to those reactors. So once an SPDK thread was assigned to a reactor, it would always run on that reactor. But what the scheduler framework allows us to do is the SPDK threading SPDK threads are designed that they can be moved between cores. Anything that you need that's local to that SPDK thread allows it to be moved between different cores. We just never had a framework to be able to actually do that. And so what we can do now is we can analyze statistics from the SPDK threads and from the SPDK reactors. We can look at the pollers that are running, and the pollers report whether they were busy, like whether they actually did any work, or whether they were idle, whether they looked for work and there was none there. And that, in combination with counting CPU cycles, it allows us to make decisions on being able to move these threads between reactors. And so what this allows us to do is, if we see that threads are primarily idle, we can move threads off of one reactor to another. If we're able to get all of the threads off of a reactor, we can shut that reactor down. We can put it to sleep, put that core to sleep. And so this allows us to realize a lot of power savings. And not just that, but even, if we have all the threads running on one reactor, we can even use things like Intel SpeedStep technology to be able to reduce the CPU frequency to get even more power savings. We've also implemented some limited support for interrupt mode, which is related to the scheduler framework that we've been talking about here. So support in vhost block with the AIO backend, the NBD front end. You're going to hear Xiaodong Liu talk about this more in one of the talks later today. And then finally, on the new feature front, zone namespace support was added to NVMe last June as part of TP4053. For those that aren't familiar with zone namespaces, this concept, started in ATA and SCSI, basically where you have zones of blocks, and these zones can only be written to sequentially. They can be read from randomly, but only written to sequentially. And this actually maps really well to NAND, where NAND is also written to sequentially, and when you want to erase it, you have to erase the entire block. And so zones can be reset so that you can then write to them again. And what it means is then in the host can actually can manage the data placement. The host understands better how the data is laid out, how the application is going to be consuming it. And so it allows us to do things like write amplification. If the host knows how data is going to be grouped and what its lifetime is going to be, it can take that data and consolidate it into one zone so that when it gets erased, we're reducing write amplification. We're not needing to do as much garbage collection. It also allows us to reduce the amount of over-provisioning on the media. So instead of the SSD needing to set aside extra NAND because it needs to do a lot of garbage collection, the host can manage that instead, and the host is going to know best how the data is going to be laid out, how it's going to be consumed, and so typically it can do a better job of managing all the media on the SSD. And so in SPDK, the work here was led by Western Digital with support from Samsung. The support goes up and down the SPDK stack. So in the NVMe driver, in the BDEV NVMe module itself, even in the generic BDEV layer. And so this allows you to build FTLs not just with the NVMe driver, but even above the BDEV layer itself, which is really nice. And then we've also added support in the FIO plugins to be able to do benchmarking of zone workloads using the support that's been added in FIO and then the SPDK plugin modules to implement that. So next, looking forward. So one of the big focus areas for SPDK continues to be IPUs, infrastructure processing units. So these are like the smart NICs that people typically call them, but IPUs are more general. It's not just NICs like networking, but it's also doing storage offload. And so SPDK is a fantastic framework to be able to implement this. We talked about the NVMe target generic layer for doing vfio-user. Well, this is really nice, also because now IPUs can present NVMe interfaces to the host, and you can build IPU-specific transports to be able to translate those and pass them to the SPDK NVMe target. But it's not just a data path. There's a lot of things, other things here as well. So telemetry is one I'll talk about here in a moment. NVMe Multipath. So being able to present an NVMe, physical device up to the host, but on the back end, being able to support multipath to, for example, like a cluster of different NVMe nodes. And we'll talk about that a little bit more as well. One of the big, areas is orchestration and management. And so, we see there's going to be a lot of IPUs coming down the road, not, from companies like Intel and NVIDIA and, different vendors, and they're going to have roadmaps. And you want to avoid orchestration engines to have to understand exactly each IPU and which, what types of RPCs are needed to configure it. And we want to be able to abstract a lot of those details. And so the idea here is having a storage management agent, something that would be developed by SPDK. You could have plugins for different IPUs, and then you could have things like a Kubernetes, like CSI driver that can talk to the SMA for a more generic interface and not have to understand all of the lower level platform details. So you can definitely expect to see more information about this coming out over the next quarter or two. Support for more host interfaces. So NVMe is one that there's been a lot of work on already to date, but we want to extend this to vert.io as well, because we still think that vert.io is going to be an important host interface for these IPUs. And then better SPDK thread schedulers. So continuing to iterate and evolve the schedulers that are in SPDK so that we can consume fewer cores when possible on these IPUs. And I think one of the other things you can continue to look at is IPDK, so the Infrastructure Processor Development Kit. You probably maybe saw some announcements on this over the last couple months. You can go out to the ipdk.io website to get more information on this. IPDK is all about enabling network and storage and other types of offloads on these IPUs, and SPDK is really the bedrock of those storage use cases on IPDK. And so I think you'll continue to see more collaboration between the IPDK and SPDK projects as well. So from a telemetry perspective, continuing to look at how do we improve the ability to debug and inspect applications that are running SPDK applications. And so I think this is important for IPUs, but it's really good for any SPDK application. And so continuing to evolve the SPDK top app. There's been a ton of work done on this already, and it continues. So being able to monitor, specifically what's happening in the SPDK application, the pollers, the threads, the reactors, their busy idle time, where are they executing? This is going to continue to be a focus area for the project. Another one is user space dtrace probes and BPF trace. So being able to instrument SPDK applications with dtrace probes so that we can, at runtime, be able to collect interesting information on how the application is running. So, for example, we've already done work for NVMF to be able to see at a very low level when we get new connections and what are the NQNs that are being connected to, and being able to monitor the states, when subsystems get paused and resumed. And there's a lot of complication in NVMF, and adding some of these probes has made it much easier for us to be able to get information in real time on how the applications are running, help debug issues, etc. And then continuing to extend the SPDK trace capabilities. So there's been a ton of work that's been done over the last year or so. Conrad Steiber from SPDK team has been doing a lot of work on this, and we'll be continuing to extend this. So, adding these traces into more of the SPDK modules, adding the ability to configure them at a much more granular level to be able to enable and disable individual trace points instead of just whole trace point groups. If this is something you're interested in, I encourage you to go out to the SPDK website. There's some good documentation on the SPDK trace capabilities, and it's something definitely to take a look at. Next is NVMe Multipath. So Shuhei Matsumoto, one of the other SPDK core maintainers, has been spending a lot of time in this area to be able to enable the SPDK beta of NVMe module to recognize and support multiple paths to the same NVMe namespace. And so then that namespace is, a single namespace is presented up to the bdev layer, but the bdev NVMe module is able to understand what is the optimal path to that namespace. And then if that path goes down, to be able to automatically transition to using a different path, so that the upper layers don't actually see any loss of service. And so there's, of course, a lot of complexity in here, and being able to do the failover, identifying the correct path, retrying the paths over time. So this is something that a lot of this work is already in the tree, but there's a lot of areas, especially around error recovery, that are continuing to be developed. And then we're also working on a discovery service. So for example, when there are multiple paths, today the administrator has to manually attach the controllers for each of those paths. But if you have a discovery service, SPDK can connect to the discovery service. The discovery service, using asynchronous event requests, can notify SPDK when a new controller, when a new subsystem is available that it should connect to. And so this is something that is targeted to land in the 22.01 release in January, where the bdev NVMe module will now be able to automatically detect when storage, or when new storage is available, or even when new paths to the same storage is available, and automatically connect to it. Next is right shaping RAID. You'll hear Wayne Gao and Yan Bo from Alibaba talk more about this later today. The idea here is having a new bdev module in SPDK that can basically take like QLC NAND with Optane to provide like a better together solution for both a performance and capacity perspective. And so the idea here is that you use Optane media to aggregate writes, and so that when you're writing to the QLC NAND, you're doing it in its optimal write size, because we know that QLC NAND has lower endurance, lower random write performance, and so we want to be able to shape. That's where the shaping part comes in. Shape the writes that are coming in into sizes that are more optimally written to the QLC NAND. But of course, we can aggregate those writes using like an Optane SSD, but then we also need to have a map of, how did the logical blocks actually get written to the physical media? And so we have this L2P map. So that's another, critical component here. And potentially down the road, this could be kept persistent in PMEM. Short term, it can be, backed up with with memory written out to the SSD. You're going to hear Wayne talk more about this in his talk. And then finally, the an async persistent memory block device. So we continue to look at ways like, how do we use the persistent memory as a high performance block device? And one of the shortcomings has been that copies to persistent memory are generally more CPU intensive than when you're copying data to DRAM, especially when you look at it from a storage perspective. Part of it is the lower bandwidth in general for a PMEM DIMM compared to DRAM, but then also the fencing operations that you have to do to make sure that the data is in the persistence domain. And so one of the things that we're working on is using the SPDK Excel framework. We already have support for doing data copies, but the Intel Data Streaming Accelerator, which will be on some of the newer Intel Xeon processors, allow you to set a flag to say, hey, this data that's being copied is a persistent memory target, and the accelerator will make sure that it does not report that the copy is complete until the data is actually in the persistence domain. And so now we've offloaded all of that off of the CPU into the accelerator, which is going to allow us to get much better performance and efficiency. And so Part of this work will be extending the Excel framework to be able to flag when those copy operations have a persistent target versus a volatile target buffer. So thanks for listening to the talk today. Hope that you learned something new. Hope that you enjoy the rest of the talks this week, not just for SPDK, but for PMDK and the performance analyzers as well. Encourage you to join the community. You can go out to the spdk.io website, see where you can connect to Slack, our mailing list, be able to go out to Garrett and submit patches. And hopefully in person, we'll be able to see you next time. So thank you, and enjoy the rest of your day.